Alright guys, so I think I'm gonna get into the same video. I'll do my best to put them together. So we're finished with the solubility chart, right? So we're gonna actually go into stuff. So just a step that you want to be, you know, follow when you're writing the equations. So write the molecular equation, including the state symbol, and make sure you balance the equation. That's gonna be a big one. So molecular equation is gonna be the ones that we're the most familiar on, the one that you have been seeing in a lab for the past, year. If any solution that are present, write the complete ionic equation include all the state symbol and all the broken up with the exception of weak acid and weak bases. So we'll talk about those exceptions when it comes up. So don't worry about those right now. If solutions are present, write the net ionic equation including all the state symbol. So we'll talk about what a net equally, what a spectator ion, and do remember the state symbol. So just about the aqueous state or solid or liquid. Final answer should be placed in the box in the AP exam where the state symbol are not required. Okay, so although it's not required for the AP exam, I do want as the best practice is to do it. It's gonna help you. It's gonna help guide you in you writing an equation. So just the best practice. Okay, this is what I mean by a lot of time. It's with our slide, it's more focusing on be able to do the problem. So if you guys want more conceptual understanding on how things work and all that kind of stuff, like what's going on, please do read the books, right? You have the recommended reading page. They're like 10, 20 pages. So sift through them, read some of them. They're going to explain the conceptual side of things better than, for us to do that. I mean, I do my best too, so you could get it from listening. So when talking about this, they're actually talking about solution of silver nitrate, yeah. So you have, basically what happened is you have the salt, right? So you have two different salts, NaCl. Just remember salt is going to be our name for our ionic compound. They're metal to non-metal, right? Metal to non-metal, metal to non-metal. So two salt and they dissolve it into water and they're gonna react, and some of them are gonna react, some of them are not. So that's kind of the situation, right? You think about it in a lab, you have two different type of powder and you have water as a solvent and you're gonna dissolve it into water so they will react. Now if they are not dissolved in water, just put two powder together, they are not gonna have our double replacement or our precipitation reaction. They are not gonna happen. Okay, and then in the course you might learn about different type of solvent too, but water is gonna be our universal solvent because it's polar. So water is gonna be our polar solvent. It's really good at pulling anything that has a plus and minus charge, and then things that are pretty positive and negative, which are all our ionic compounds. It's not gonna be as good a solvent as anything that is non-polar. So a lot of molecular compound is gonna be non-polar. So, but it's gonna be one of the best solvent, right? That's how life started in water. Anyway, so with that said, let's dive into the question. So what is the molecular equation? So I'm gonna simplify the molecular equation. It's gonna be our silver nitrate, so NO3, so known as aqueous, plus our sodium chloride. So I mean those are just the given, right? They let us know that those are the two that they're gonna react with each other. So we assume that they do react and they're gonna replace each other, right? So the metal is gonna change places. So we're gonna NaNO3 aqueous plus our AgCl. So I do gonna put solid because I know that is gonna be what participates out. And you also know that as well. So if you refer back to your solubility chart, right, you could flip back to that on your notes. You'll see that Na sodium is gonna be our group 1 metal. NO3 nitrate is also gonna be our on the list of it for sure. It's gonna dissolve into water and stay dissolved. So going back to the list, one thing I forgot to mention. There's only 3 times that those 3, right on the pink one, those 3 is gonna be out of the water. Is gonna be when you're super saturated them and you evaporate the water. So think about like seawater. If you evaporate the salt, it's gonna come out, right? But in another case, when you have enough solvent, so enough water, they should stay in the water. Okay, so that is it for our molecular. Complete ionic is they're gonna assume anything that's aqueous is dissolved. So that's why I want you guys to write down the aqueous state so that we could know that for sure those are gonna be dissolved. So again, right, you can see that it's the solid right here. That's gonna be the solid, and this is the aqueous solution. So we are only looking at really the aqueous solution. Our solid, our precipitate is gonna stay the same. So complete ionic. Okay, so we have to separate those into ions. So if we forgot to mention what ion is gonna be our positive and negative charge molecules or atoms that is in our solution. So they are not gonna be I don't think that I was going with it, but I forgot. But anyways, so you have the positive and negative charge ion that's in the water. So in this case, it's gonna be Ag plus aqueous, so plus our NO3 minus aqueous. So in this case, you can see that they remain positive and negative. So if you think about it, they are right in a solution. They are gonna be free flowing around in our solution. So they're not gonna be bonded together. Once they're in a solution as a salt form, they're gonna dissolve, right? That's hence you don't see them as a powder form anymore, right? It's just like it dissolving, table salt. You don't see the actual salt. They're being dissolved into the ionized form. So ionized form has to have charge, right? Or the ion has to have charge. They're not gonna become their neutral state. How do we know that? Because if it's the neutral state, sodium, metal, in its neutral state is really reactive water. So it's going to form H2, right? It's going to combust. And you don't see that when you dissolve your table salt, which is made of potassium and sodium. So those are alkaline metal that's really reactive. So we knew that they has to be in the ionic form, the ion form, when they're in their solutions. So keep that in mind, right? They are ions. Ions are basically staying. Those are the things that come off from an ionic compound, right? So they're in water, they dissolve. Because they are positive and negative, they are gonna be pulled apart, right? They are polar. They're gonna be pulled apart by the water. Remember, right? Remember last year, water is gonna be slightly positive and negative. So they are gonna be pulled apart, and that's why water is such a good solvent for anything that has charge. So we finished with our reactant side, then we have it with our product side. So again, Na aqueous plus our NO3 minus aqueous. And lastly, we're gonna have our silver chloride, and they're gonna be in its own form, in their own solid form. Okay, because they all are bind together to form a solid, so we are right? They're not ions. They're not in the water. They're not aqueous form. They're in a solid form. They combine to form a compound. Right? It's also salt in this case, but it's gonna be stronger than the pool. The attraction between silver and chloride is gonna be stronger than the pool from the water that surrounds it. Therefore, it's gonna stay as a solid instead of being dissolved into water. Okay. So for this step, we're gonna have to find our net ionic equation, and that's where the spectator ions come in. So spectator ions are the ions that was not involved into the reaction. So most of the ions that we know is completely dissolvable or soluble into water. So the group 1, nitrate, NO3, and ammonium is gonna be the spectator ion, and also along with other things. So basically, the way you could find out is that if they're present in a reactant and they're also present in the ion form in the product, that means they were not involved, right? So, think about a beaker or reactant, right? They were present in the beaker, and the same amount is also present after the reaction. That means they were not involved into the reaction. Now, does it mean that they're not important? No. It just means that, right, they're important in the sense that they're bound together and those are the salt they form, but not important in the sense that they're not involved into the reaction. So in our case, we have our sodium. We have our sodium on both sides. They're the same. We have our nitrate on both sides, and those remain the same. So think about, in algebra, think about you have x, y, z equal to, x, y, o, right? In this case, you could kind of cancel out the x and the y, right, on both sides because they are gonna be the same. So this is kind of what it's gonna be like with our ionic reaction. So I'm gonna erase this. So do come back if you do need one. So our net ionic, right? So only taking out what is the excess or what is unimportant or what is did not react. Then we are only left with our silver ion plus our chloride ion going into silver chloride solid. So that's gonna be our net ionic. So that's what you're gonna put on your AP test. Yes, you could omit the state symbol, but I would include it for the best practice. It does show that you knew that is precipitate, but you don't need that for your AP test. Okay? Right here. So this is what it is. This is our complete ionic. Notice, right? Remember what I'm talking about, the X, Y, Z, L. Let's say those are the 4 variable. And then if you also have X, Y, O, then these 2 you could cancel out because they were present into both sides of the reaction. And in this case, again, NO3, Na are present on both sides, so you could cancel them out, resulting in our net ionic. Okay, this is also going to be important particular diagram. This is, I think this is a little bit new, not where we're at. They just want you to visualize how it happened. At the end of the day, the bottom is going to be the same. So silver chloride is also going to be the same. It's really, the other thing is going to be different. Do be very careful. You do have to read this nice and clear. NaCl solution works in excess. So we should see Na ion and chloride ion in there. And in this case, we don't see this here, so we could cross that out. We do see this here, and we also do see this here. So the difference between these two is that it has a silver ion in there. And remember, talk about how silver and chloride have a really strong attraction. So if more attraction than if they were in the water, that's how they precipitate out. So if you see this and you also see a chloride, they are gonna react so to form this. So we know that if we see the two ionic form in there, that is not gonna be it, right? They would have reacted and formed our precipitant, and this is gonna be our correct particular form. So the NaCO exit and still has spectated ions presented in the solution. Okay, so let's do one more. We have our ion nitrate and add it to a solution of potassium hydroxide. So we are gonna have this for our lab as well. I did order some of those, so we're gonna have some fun, and you're gonna see the reaction that we work with, present in your lab as well. Okay, so molecular formula is gonna be our ion NO3 plus our potassium hydroxide, and they are all gonna be in our aqueous solution. Going into these two is gonna switch place, so we can have our KNO3 here plus our ion hydroxide. I'm gonna add in the state right here. Notice this case, second question, this additional step we do have to balance them. This is ion 3, so ion 3 plus, right? So we're gonna have to have 3 hydroxide in order to balance that out. So hydroxide is gonna be 1 minus, so 3 of the hydroxide is gonna balance out the charge. So do kind of keep those in mind that you do have to balance them. Okay, now we have 3 OHs, then we're also gonna have to have 3 of the potassium hydroxide. So we should have 3 of the K, and it match up, right? Because we have 3 NO3, 3 NO3, 3K, 3K, 3 OHs, 3 OHs. So this is gonna be our balanced molecular equation. So keep those in mind, right? So this is a video, so you can always go back to it. I just ran out of space. Now we're gonna work on our complete ionic. So then this two is gonna be our aqueous, and then we have our our ion hydroxide is gonna be our solid. I think I messed up on the previous one. So let's work on the left side, right? So these two, because the aqueous, they should dissociate into ion. So we have our ions, iron, Fe ions plus our nitrates ion. It does get a little bit tedious writing all those out. Plus our potassium ion plus our hydroxide ion. Going into, right, our potassium ion going into our nitrate ion. So these two are, referred to as solubility chart. They are going to be always dissolving into water. Okay, and then lastly we have our particulate or precipitant, which is our ion hydroxide. So this should be solid. So the previous molecular formula I did mess it up. So this should be solid. Okay, so that's gonna be a complete ionic. Then our net ionic is gonna be canceling out the spectator ion. So these two are the ones that we're gonna cancel out. So our net ionic, I'm gonna try to write it right here. It's gonna be our ion 3 plus aqueous plus our OH minus aqueous going into ion hydroxide. Okay, I know some of you guys say, well, they forgot to balance it. Yes, I forgot to balance it. So when you balance it, do be just very careful. So let's look at this one, right? So you should have 3 OHs, so we should have 3 of this. Yeah. And if you just look at the complete ionic equation, that's all you need to balance, right? But refer back to our molecular equation. You should have it in a guide to know you're a little bit more space. You see that we should also have 3 of this, 3 nitrate on both sides, also 3 potassium. So when we're balancing our complete ionic equation, we are going to balance it according to the molecular reaction, because we're not just putting ions in there individually. They were a salt first, so they have to be proportion, right? You have to have, for every nitrate, you have to have 1 potassium. They were the salt together. Okay, so, but for our net ionic, this is it, right? Because we cancel out our nitrate, and then we also cancel out our sodium. Okay, so let's read number 2. Select the correct particular diagram that best represents the reaction if stoichiometric proportion amount of the reactant are aggregate. So in this case, right, the main difference is going to be our stoichiometry proportional amount. So what that means is that they use the exact amount. So, right, the number of reactant react perfectly with the number of reactants. So they have exactly every, for every ions, it have 3 nitrate ions, so they were exactly proportional. So that's gonna be different from our excess. I tried to make the video before this, and that's where I kind of messed up. So let's look at those, right? The solid is gonna be the same, so we cannot rule out anyone just from the solid itself. So in other words, if you look at a particular diagram, it's also gonna give you clue to which one is gonna precipitate out. So maybe use that to your advantage. Okay. So so this one, we know that if both ion and hydroxide there, they should bond together, right? Because they should have a greater bond. Therefore, they will precipitate out. So we're not gonna have number 3. Now you're between number 1 and number 2. So I'll pause a little bit and see if you can figure out which one should we have. Okay, so the answer is B. So if the question is talk about excess KOH, right? KOH. Yeah, excess KOH. Then this will be the case. But it's a completely proportional, stoichiometric proportional. So we assume that there's no more hydroxide left. Okay? So I do notice this KOH. So when we refer back to this, then think back that it should be, they have to be proportional, right? If you have 3 OHs, because the K is with the OH as a salt, then you should also have 3K. And so always refer back to molecular formula when you're doing your complete ionic formulas. The aqueous, so the state, you don't have to put it for the AP. But so notice how they also are balanced, not according to the complete ionic, but according to our molecular formula. Okay, the standard diagram is correct if the reaction is done stoichiometrically proportional. That means that all the ions for ions and hydroxide are the propellant, and only the spectator ions remain. Okay, and one of the things is that they're not electronically neutral, so you do want to make sure the charges add up. So that might give us another clue for which one is the real deal. So for the trial, we're gonna also have to draw them out. This is actually part of the AP test. They do kind of ask you that, right? So that you could I think the key, right, the reason why they want to do it is want you guys to visualize what happened in the solution compared to just knowing it from the formula. So given the following scenario, an excess solution of potassium iodine Ki is added to the solution of lead nitrate. So notice they use nitrate and potassium. That's something that I noticed right off the bat. So those two are gonna be completely soluble into water. Okay, so let's try to draw the diagram. So in this case, then these two are gonna switch, right? These two metals gonna switch. So PBI PBI2, that is gonna be our solid and our precipitant. Okay, so make sure you balance out the charges, right? PB, you have 2 nitrate, so we know that is 2 positive. So you also need to have 2, it tells you 2 iodine to balance it out. So, right, that's going to be your practice of writing out all the molecular completely and ionic, like ionic. But the diagram is what we're going to care. So in this case, is the excess solution of potassium iodine. So again, we have to know the salt first. So the salt have to be PBI square. So that's going to be our salt. So we're going to have excess amount of potassium iodine. So we're going to have some iodine in our aqueous. Do we have to write down aqueous? No, we just have to draw them a circle, right? We do going to have them iodine circle in there. So the size matter. I'm going to look it up for you guys about the size of the particulate. But Jordan proportionally, so later on in the periodic trend, we will look at the trend for atomic radius. So in that case, you should have a better idea. And also, if they have more than one atoms, that's gonna be bigger than you only having one atoms, right? So in example, like I should be smaller than our NO3, right, our nitrate. That's just right because you have 3 oxygen versus 1 iodine in this case. But also, like, it's not always absolute. So always, when we look at our periodical trend, we'll look at our atomic radius. So again, we should have those. And let's look at what are the spectator ions. So again, right, stuff that completely dissolve our potassium. And nitrate is always going to be looking at us in the water without reacting, right? We refer back to the solubility chart. They will remain in water. So we could just draw those out. And we should be good. So 2K, so those balance out. And then we do have... Wait, so it's excess amount of Ki. So I'm going to add one more K right here. So then we'll be... Yeah. Ki, 2K, 2I. Okay. 2K, 2I square. So should we have extra left? So 2K, 2K. 2 NO3. Okay, let's see. Because my question right now, I haven't done it that much before. So my question right now, do we have to make it electron neutral, or the charge neutral? Charge, right? Like basically 0 charge. So in this case, right, this will be 0 charge, right? They all kind of balance out. But I'm also thinking about, we have the excess solution of potassium iodine. So we have extra I and extra K. That should be fine as well. So I think this should be the final answer. But didn't really show it. The diagram answer. What? They really don't show it. Let me look at the notes real fast for this slide, particularly. The notes for this one. Okay, so corresponding PBIs must have K plus and NO3 must also be electronically neutral. So that's what we were talking about right here. So where they have to balance out. As always, one of our students after handing up the newsprint, try should have student complete this on the newsprint class. I remember the positive ions are typically smaller than the negative. That isn't essential for it to be correct. So yes, the one that we did is gonna be correct. It have to be electronically balanced. Okay, so we are gonna work on those later. So you have acid and base left, and then we have our acid to carbonate atom left, particulate matter as well, and we have our oxidation and reduction. So quite a lot to do. Okay, so we'll get through them. Stay tuned. We'll get through those things as time goes